Hello and welcome back to Unit 4. So this is still bistable elements and clock synchronous sequential circuits. We are now on lecture 6 and we are going to discuss here design with unused states and design with counters. So let's take this certain example. So we are given either this state table on the left or its equivalent state diagram on the right. So in this particular example, we have here SR flip-flops, and we are going to use 3 of them, A, B, and C, and A, B, and C. So SR flip-flops are not very common to use because we have the JK flip-flops, which have much more flexibility and practicality in terms of 4 valid states. But for the sake of discussion, let's just consider this as it is, SR flip-flops. Now, since we have 3 of them, A, B, and C, so we're supposed to have 2 to the power of 3 or 8 states. But if you take a look at the state diagram, for instance, you have here 1, 2, 3, 4, 5 states. So we have 001, 010, 011, 101, and 100. So which means that we have 3 unused states. So by comparison, we can determine that we have unused states 0, 000, 6, or 110, and 7, which is 111. So if we have such an example, the design process at the start is very similar with the rest of the other types of examples that we have discussed recently. So we start with either the state diagram or the state table. And the next step would be to get the flip-flop input columns and get its simplified function. Or we use a K-map so that we can obtain a simplified function for each of the flip-flop inputs. And from there, we're supposed to derive a new state table that would include the unused states that we have already identified. So let's start. So first is we get the flip-flop inputs. Now, if it's not indicated in the problem, we're supposed to treat unused states as don't cares. So which means that they can either have 0 or 1 because it doesn't matter in our original problem. So to help in the simplification of the functions, we must treat them as don't cares. So we mark them as X's in the K-maps. So from the state table, we are going to derive the simplified flip-flop inputs, which we can derive using K-maps. So here, we are going to mark them first. So take note that in our K-maps, aside from using just the present state, we're also going to consider the input. So which makes our total number of inputs for the K-maps to be A, B, C, and X, 4 of them. 2 raised to the power of 4 would be 16 squares. So we have 4 variable K-map here. So let's map out the don't cares first. We consider states 0, state 6, and state 7. And based on our truth table, the least significant bit is X. So which means that this can either have 0 or 1, this as well, and this as well. So in our K-maps, that would mean this is here 0, 1, 1, 1, 0, 0. So here 1, 1, 0, 1, which is here. Next we have 1, 1, 1, 0 here, and 1, 1, 1, 1, which is finally here. So remember, we have this shaded squares marked with red X's. These are the don't care values based on the unused states. Now let's plot our flip-flop inputs. So our flip-flop inputs were initially recorded, but in the case that this is blank, then we can use the SR excitation table by looking at the present state and the next state, and we can use the excitation table to plot out these values here in the flip-flop inputs. But assuming that we already have this one, now let's consider SA and RA so that we can both get their simplified logic functions. So we have SA here and RA here at the bottom. Plotting out first SA. So we have this minterm 1 here. This is at 0, 1, 0, 1, which is located here. And we also have this one here. So this is 0, 1, 1, 1, and that is found here. And we also have 3 other don't care values in SA, which came from the excitation table of the SR flip-flop. So we plot that as well. And finally, since everything else is 0, then we don't need to put that here. And then we group the essential prime implicants that we can find in this particular map. So in this case, we must make sure that the ones would be grouped together. But since we also have the don't cares here, we can expand that group into 4 minterms. Okay, so this one here is B and X. That's why we have this function. So we do the same with RA. Plot the ones and plot the X's already here in RA column. And together with the unused states that we have identified earlier. So here the red X's are the don't care conditions caused by the unused states. And then we group here. So therefore we have CX prime. And then we continue to the next one. Let's consider B flip-flop. So SB and RB. So at the top we have SB and at the bottom we have RB maps. First, we map out the don't cares caused by the unused states that we have identified. Then we map out for SB. We map out the minterms 1 and the don't cares here. So finally find the group. So we have this group. And then finally we have this simplified logic function. We do the same with RB as well. Plot the unused states. Plot the minterms, the ones. And then plot the don't cares in this column as well. And then find the essential prime implicants. So we have 2 here. And we have this function as well. Next, we have flip-flop C. So again, it's the same process. It's just reiterating. So we have here the unused states, the red X's. Then the minterms in SC. And then the don't care conditions in this particular column. Find the simplified logic function and then you proceed with the next. So RC as well. And finally, since we have an output, then we need to do the same thing with the output. The don't care conditions caused by the unused states, and then plot the ones. And since in this particular column there are no don't cares here, there are no X's, so that ends this map, the plotting of this map. And then we group. So we have this one here, and then that's AX. So in the design of a sequential circuit without unused states, we can now directly obtain the logic diagram, and that's it. But in the case of designing with unused states, especially when we treat that as don't care values, then we need to analyze the circuit again, because since we are introducing the don't cares here into our function, then they must have an effect on your final design. So which means that we have to make a new state table, which would now include the unused states. So in this case, again, we have unused states 0, 0, 0, 1, 1, 0, and 1, 1, 1. And if we plot all of the total number of inputs, which includes the present state of the 3 SR flip-flops and 1 additional external input X, so we have a total of 2 to the power of 4, which is 16 input combinations here on the left side of our state table. So take note that we have marked here in red the unused states that we have. And the black ones here are the valid states that were being represented in our original problem. So first, what we do is, based from the flip-flop inputs from the K-maps, we determine the effects of the unused states by creating this new state table. And we use the flip-flop inputs and output functions from the K-maps that we had just did a couple of slides ago. So this is a summary. We have SA, RA, we have SB, RB, SC, and RC, and lastly the output function Y. So what we do is we use the function for SA. For example, this is BX, and since BX is in SOP form, then we can find B and X to be 1, 1 for that particular combination, and we find that here. So BX 1, 1, so we have here B is 1, X is 1, and therefore we have a minterm here. And we find another pair here, 1 for B, 1 for X, and that's another minterm here. In the last two, we have B is 1, X is 1, this is 1, B is 1, X is 1, and the minterm is 1. So that completes this function, and since there are no more other terms, we mark the blanks with zeros, and that completes SA. We do the same with the rest of the functions. So RA, SB, RB, SC, RC, and function Y. So once we have completed our flip-flop inputs, then we move on to the next step, which is to encode the next state value. So this column. The purpose of this is to check the valid states, so the states in black. So we check the valid states if they have the same next states as the original state table or the state diagram, so which was given in the problem. So you have to check if they have the same ones, because if you don't, it means something went wrong in the K-maps in obtaining the logic functions. Another purpose of this one is to obtain the next state values of our unused states, which is important as well. So what we do here is we use the flip-flop inputs, so this column, and the flip-flop characteristic table. So since we are using SR flip-flops, then we use the characteristic table of our SR flip-flop so that we can get the next state values. So in our characteristic table, we have the SR inputs, and then we will know what the next state is. Going back to SA and RA, so we consider one flip-flop at a time. So this is 0, 0. So 0, 0 is no change. So we follow the present value of flip-flop A. So 0, this is 0. Next is 0, 0, which is still the same. Present state 0 would be the next state value. And we do that with the rest. And let's continue from the other unused states. This is still 0, 0, no change based from the characteristic table. And then we get the present value of A, which is 1, and that would be the next state. Next one is 1, 0. This is set. So the next state value is automatically 1. Next, 0, 1 is reset based on the table, the characteristic table. And then, since it's reset, then the next state is automatically 0. This one is a set again, so this is 1. And we do that with everything else. So once everything is filled out, then we can check the valid states if these are the same values with our original problem. And then what we do next is to look at the unused states. What are their effects? So what we do is, based from the new state table, we verify the states. And once we verify, we are going to make a new state diagram to show the unused states, where they go. So these next states of the unused states must be one of the valid states, and we call that a self-correcting design. Because take note, unused states, from its name, we don't use that in this particular problem. In this particular scenario, they don't exist. But to aid us in our designing process, we can insert them as don't cares. And then we have to make sure, in the event that the unused states become a present state, for instance, they must be able to return to the original sequence or one of the valid states. So it must be able to self-correct. So once we have the new state table, what we do is we consider the present state, where it goes, and based on the input. So if we have the valid states and they have the same next state values as with the original problem, then this must be the same. This was already given at the start. So if this is okay, then we can just look at the unused states. So let's consider unused state 0, 0, 0. There are two inputs, so which means they go to two different states. So we might have two arrows here. So the next state is 0, 0, 1 if x is 0 and the output is 0 as a consequence. So here, let's mark this as one of the unused states. It goes to 0, 0, 1, so marked by this red arrow here. The input is 0 slash the output 0. Next, if the present state is still 0, 0, 0 and our input is 1, then it goes to state 0, 1, 0. 0, 1, 0 is here, so that's why we have this red arrow marked by 1 x slash y, which is 0. So next we go to the other unused states. So let's take 1, 1, 0 first. So if input is 0, it goes to state 1, 1, 1. So we have this line here. So that happens if input is 0 and the output is 0. So that's why we have 0 slash 0. Meanwhile, if input is 1, it goes to state 1, 0, 0. And the output is 1. So here, we have 1 slash 1. And finally, the last unused state, we have 1, 1, 1. Input is 0, it goes to 0, 0, 1. So we have this line here and marking that with 0 slash 0. And lastly, 1, 1, 1. And if input x is 1, it goes to 1, 0, 0. So here. And we mark that with input x1 slash y1. So here, 1 slash 1. Now I want you to take a look at the state diagram closely. So you would know that these are unused states because there are no incoming arrows going into them. But in the event that the present state is one of them, they must be able to go back to one of the valid states, which is this ones here. These are the valid states. So if the unused state 0, 0, 0 becomes the new present state, on the next clock pulse, it must be able to go to one of the valid states, which is true in this case, because either of these two states are valid states. In the event that 1, 1, 1 becomes the present state, on the next clock pulse, it goes back to either 1, 0, 0 or 0, 0, 1, which are both valid states. So that is correct. In the event that we have 1, 1, 0 and the input is 1, it goes to 1, 0, 0. So that is still a self-correcting pattern. However, if we have a 1, 1, 0 and the input is 0, it goes to another unused state. Now, after this becomes the new present state, the next state would either go to this state 4 or this state 1. So which makes that still a self-correcting pattern. So the only way that this would become non-self-correcting is that when two or more unused states would never go back to one of the valid states. So that might happen if we have 1, 1, 0 goes to 1, 1, 1, and after 1, 1, 1 it goes back to 1, 1, 0, such as a never-ending loop here. So in the event that happens, then our circuit will never go back to the original valid states. The only way we can probably correct that is to reset the design. But we want a self-correcting design such that we need the unused states to be able to recover to one of its valid states. So in this particular scenario, this is okay because after going from 110 to 111, both of them unused, from 111 it goes back to one of the valid states, which is what we want to happen. So after we verify a self-correcting design, then we can now complete the design process. So once we verified everything, the valid states, so they go to the same next states as given. And for unused states, they must be self-correcting. So to recap, we have started with a state diagram or a state table. Using either of the two, we have noticed that we have unused states. So after that, we use the flip-flop inputs and get the simplified functions using K-maps with the aid of the unused states. So since we are using unused states, we don't know where they go to. So we need to analyze the circuit. And what we do is we make a new state table through analysis. And then we verify the valid and the unused states, which are described here, what we are supposed to do. And once we have verified everything, especially that it is a self-correcting design, then we proceed with the new state diagram and finally a logic diagram. So we have this logic diagram here, which is based on the flip-flop inputs that we have derived from the K-maps. So in the event that our design is non-self-correcting, we must change something in the logic functions. So what we do is we might regroup the minterms and the unused states in the K-maps. So in the event that that will happen, then this might change. And if this changes, then our new state table might change. But in this particular example, we have verified that our design is self-correcting, then that means this must be correct. And we finally have our logic diagram based on these functions. So now let's go to the next topic in our lecture, design of counters. So counters are sequential circuits using flip-flops that would follow a specific given sequence. So in this particular example, we have a 3-bit counter, so which counts up. This is a binary counter. We have 0, we go to 1, 2, 3, 4, 5, 6, 7 being the last of the 3-bit values, 111, goes back again to 000. So the design process of counters is still the same with the design process of sequential circuits using flip-flops. So we may start with a state diagram such as this one, or a description of the counter that we're going to design, and we derive the state diagram based on the sequence given. Once we have the state diagram, we now derive the state table. So what we know from a state diagram is that we have the present state and we have the next state because of the arrows designated between them. So if this is the present state, this is the next state because of the direction of the arrows. So we can now fill out the next states. So here we have 0, the next state is 1. If the present state is 1, the next state is 2, and so on. From 111, it resets back to 0. And since this is a 3-bit counter, then we must assign 3 columns for present state and 3 columns for next state for the designation of our 3 flip-flops. We can name this as any variables that we want. But in this particular case, we have A2 as the most significant bit, A1 and A0 as the least significant bit. In this particular example, we don't have external inputs and external outputs. In the case of counters, having present state and next state is already sufficient because the states themselves would be represented as the outputs of the counters. There are also cases wherein we may have external inputs, such as an enable input, or we might have an external output, such as a counter complete output. But in this particular example, we don't have any, so this is already sufficient. Now, in order to proceed to the next step, then we must have the flip-flop input columns here to represent what are the inputs that we need for our T flip-flop to transition from present state to next state. And for that, we use the flip-flop excitation table. So in this case, we are using a T flip-flop. So therefore, we get the flip-flop excitation table for the T flip-flop. So if we have this as the present state, and then this is the next state, then this is the corresponding T input that would make that happen. So in the event that we have 0, and then the next state is 0, then we'll use the excitation table, and the T input is 0. So that's why we have a 0 here. The next case is the same, 0, 0, 0, 0. So both of these are also zeros. Then the next here is 0 goes to 1, and based on our excitation table, the result is 1, or the T input is 1, so that's why we have a 1 here. And next we have a 1 and a 1, so that is a 0 at the T input, so this is 0. So the next two cases are also the same, so that's why these are 2. And the last would be 1 to 0, so 1 to 0 has a T in input equal to 1. So we do the same for flip-flops A1 and flip-flop A0. So once these columns are complete, then we can proceed to obtaining the simplified flip-flop input functions, which we can do through K-maps. So based on our state table, we have 3 flip-flops for our present state. And since we don't have any input x, then this would represent the total number of variables that we need to have as inputs on our K-map. So we have 3 variables here. That's why we have 3 variable K-maps as well for each of the flip-flop inputs. So taking, for example, the most significant bits, A2. So we look at TA2 here, and we can plot the ones, the minterms in our maps. Now, since we don't have don't care conditions here, then this process is a bit faster because we just look for the ones. So this is minterm 3, and the last one is minterm 7. So plotting that on our map, we can group these two together. Then we get our function as A1, A0. Next, we proceed to the next flip-flop input, TA1. We have 1, 2, 3, 4 minterms. We plot that in our map, and we can get these 4 minterms grouped together. This is A0. And finally, we use the last flip-flop column. So we have TA0, and looking at our minterms here, which are all the combinations that we have for our 3-bit inputs. So we don't actually need to map this out because this is just equal to 1. But for illustration purposes, here it is. Now we have the simplified flip-flop input equations. Then we can now draw the logic diagram based on these inputs. And here we have our 3 flip-flops. Don't forget that all of them are connected to the same clock source, and we can designate each of these present states into the Q outputs of the T flip-flops, and we use the simplified T flip-flop inputs to complete our circuit. So now let's consider another example here. So this is still a counter, but in this case, we call this the non-binary sequence because it doesn't follow the natural binary sequence that we have, such as in the previous example. So we look at the state diagram given. So we have 0, 0, 0. It goes to 1, 2, 4, 5, 6, and goes back to 0, 0, 0. Now, I want you to take note that we did not have a state 3 here. And we don't have a state 7 here. So which means that these 2 states are unused states. So if we plot our first part of our state table, we use the state diagram to follow 0 to 1. So we have here 0 to 1, 1 to 2, 2 goes to 4, 4 goes to 5, 5 goes to 6, and finally 6 goes to 7. Now, since we are using 3 flip-flops here, A, B, and C, then naturally we should have 8 combinations here, right? But since we did not find any state here belonging to state 3 and 7, then we must consider these 2 as unused states. If the problem did not say anything about these missing states, then we must treat them as unused states. So following the design with unused states, we proceed now to our flip-flop inputs. So in our flip-flop inputs, we use the excitation table. In this particular case, we are using JK flip-flops. So since we have 3 flip-flops, then we must have 6 inputs for each of the J and K inputs for each flip-flop. Using the excitation table, so present state 0 and the next state is 0. We looked it up. 0, 0 is 0x, so we have 0x here. Still the same. 0, 0, this is 0x. Next, 0, 1 is 1x. Next, 1, 1 is x0, following the excitation table. This is 1, 1, still the same, x0. And finally, 1, 0, x1. And we do the same for flip-flops B and flip-flop C using the excitation table. So we now have our complete inputs here in these columns. So the next step is to derive the flip-flop inputs. Now in this particular example, I will leave this up to you to create the K maps for the J and K inputs for all 3 flip-flops. But again, remember that we did not have unused states here in our table, so it's okay that we don't have it here, just as long as you remember to put them in our K maps. Map them out as don't care conditions so that we can have simplified functions. These are the simplified flip-flop input equations here, and based on this one, we must be able to check what the effect of these unused states would be in our design. So just like the example with unused states, we must make a new state table by analyzing the circuit again through the flip-flop inputs so that we can plot what are the next state values for our unused states. And then we have a new state diagram. And finally, we have the logic diagram. But again, the purpose of having the analysis procedure here by creating a new state table and a new state diagram is we can verify the valid and the unused states. And if our counter design can be able to go back to any of the unused states, we call that the self-correcting counters. So again, these are unused states that go back to the given counter sequence or any of the valid states of the counter. So here, based on our new state table, we can now have our new state diagram. And from there, we were able to derive the next state of unused state 111. We derive its next state to be 000. And another unused state here, 011. Its next state is 100, going to here, and goes back to the original sequence. So in the event that the counter goes into any of these unused states, the counter should be able to return back any of its valid states, therefore making it a self-correcting counter. This is our goal. And since this is already a self-correcting counter, then we can now complete our design by creating the logic diagram based on the flip-flop input equations. So this ends our discussion for lecture 6. And also, this marks the end of Unit 4. Please answer the following exercise, and we will see you again in our final unit, Unit 5. Thank you very much for listening and watching.